also told you that you should favor composition as a priority. And the list of substitution principle talks about polymorphism, and that's an important aspect of understanding how to go about composition. So the reason it's called the Liskov substitution principle is because it's named after Barbara Liskov, who originally back in the 70s described this principle. And she described it in very mathematical terms, so if you read the original paper by Barbara Liskov, it's mostly in Greek letters. And I must admit that I have myself tried to skim that paper, but didn't really understand what it was trying to tell me. And that's probably a very common feeling if you're trying to read literature papers. So Robert C. Martin tried to make this a little more understandable for us by saying subtypes must be substitutable for their base types. Now, if this is the first time you see this and you've never heard about the Liskov substitution principle before, this may actually not help you a lot. I don't think that this way of phrasing Liskov substitution principle is particularly more helpful. It's more helpful than the Greek letters, but it still sounds very abstract. In the end, I think the best way to learn about the Liskov substitution principle is to see lots of code examples. So see examples of how you adhere to the Liskov substitution principle, and to see examples of when you violate the Liskov substitution principle. But still, I'd like to propose a different way to try to explain the Liskov substitution principle by saying, if you imagine that you have a client, that client should be able to consume any implementation of a given interface without changing the correctness of the system. So there's a little bit of new terminology here, because what does the correctness of the system mean? Notice that I explicitly do not say that we can't change the behavior of the system. The polymorphism is all about changing the behavior. In the end, the correctness of the system is application specific. But you can think about the correctness of the system as the superset of all the correct behavior that the system can exhibit. So different behaviors might represent variations in how you want the system to behave. And the superset of all legal behaviors in the system forms a sort of boundary of the system and saying, well, if you stay within that superset, if you stay within that boundary, you haven't changed the correctness of the system. But if you go outside that boundary, then you change the correctness of the system. But the correctness of the system is essentially application specific. I think there's only a single universal rule we can say about the correctness of the system that at least applies to the vast majority of all systems. And that is, the system should not crash. That is most likely a very universal rule. You probably can't counter examples, but for the vast majority of all software, the software is not supposed to crash. So what this means is that if you have a client that talks to version A of an interface, and that's not cause the entire system to crash. If that client changes to talk to an implementation B of the interface, and that causes the system to crash, then you have changed the correctness of the system. But if implementation B of the same interface also does not cause the software to crash, then you probably haven't changed the correctness of the system. We don't really know because, again, the correctness of the system is application specific, so even if it doesn't crash, it may still exhibit incorrect behavior. But at least we can probably say that if the system crashes, we have changed the correctness of the system. So that's at least the lowest common denominator that we can talk about when we talk about the correctness of the system. When is the Liskov substitution principle violated? There are various telltale signs that will indicate to you when the Liskov substitution principle is violated. Possibly the most common and the most easy one to spot is if your code throws not supported exception. Code throwing a not supported exception indicates very strongly that there are parts of an interface that's not supported, and that will also very strongly indicate that the correctness of the system is in jeopardy because there are members of an interface that cannot possibly work correctly. My favorite example is from the .NET framework. So the .NET framework defines various collection types, collection interfaces, collection classes. And one of the collection interfaces is iCollection of T. iCollection of T defines various members like add, clear, contains, copy to, and so on. It also derives from the iInvolve interface, which means that a client can work to iCollection of T interface and integrate over all the elements of the There are various implementations of this interface, like list of T, collection of T, and so on. And there's one implementation that's particularly interesting, which is the read-only T. The read-only collection of T is obviously a read-only collection, which means that once the collection has been initialized with this set of initial values, you can't change the collection afterwards. So you can't add or remove items from the collection. Now, read-only collection of T also implements collection of T among various interfaces that it implements. It also implements queries like the contains method or the copy-to method. The read-only collection of T class just does what it's supposed to do. But because the iCollection of T interface defines various members, and it's only possible to implement an interface in its entirety, there's this problem with the add and the clear and the remove methods, because the add method is supposed to add an element to the collection. The clear method is supposed to remove all items from the collection, and the remove method is supposed to remove a particular item from the collection. But you can't do that if you have a read-only collection. So instead, what the read-only collection of T actually does is throws the new logical exception from those methods. And this raises the risk of substitution question, because if you have a client that was talking to iCollection T, so you have a client that communicates through the interface, and if your system so far had been running by implementations where it was really talking to list of T or collection of T, and everything worked fine, and then later on you decided to change the implementation of iCollection of T into a read-only collection of T, there's a risk that this system that works fine with list of T or collection of T would now start breaking with read-only collection of T, because if it calls add or clear or remove, that would now result in a logical exception. So that raises the correctness of the system, because before the system would be running without any exception being thrown, and then afterwards the exception will start being thrown. So if you have not support exceptions in your own code base, that strongly suggests that your code base is violating the risk of substitution principle. And in this case, we saw that the .NET framework actually violates the risk of substitution principle. This is not the only example. There are more examples, but this is probably the most famous one. Other ways you could violate the risk of substitution principle is if you have lots of down classes in the code. If you try to check, for example, whether an implementation of iCollection of T is actually a list of T or is actually a list of T, and you do various different things based on the downcast and how that downcast evaluates different types, then you may also be breaking the risk of substitution. That smart guarantee might actually be able to do that and still adhere to this risk of substitution principle. What you have to do in that case is then make sure that there is a sensible fallback rule, so if the implementation of the interface that you're talking to does not match one of the concrete types of the testing, then you're still doing something proper that can handle the type. Still, there seems to be a correspondence that if you have attended downcast, it probably indicates that you should put at the risk of substitution principle and see whether or not you could design your system in such a way that downcast is not necessary. And the final way that sometimes the risk of substitution principle can violate is if you try to extract interfaces. So this is a more subtle, but actually turns out to be perhaps the most common way of violating the risk of substitution principle. I'm going to show you some examples later on. But basically what I mean by extracting interfaces is that in many IDEs, you can extract an interface from a concrete class. So for example, in Visual Studio, you can point to a class and then you can tell Visual Studio that you want to extract an interface. And it's going to pop up a little dialog box for you and say, well, what do you want to call the interface and which members of the concrete class do you want that interface to assign? And it's very easy to just say, well, I just want to have all members of my concrete class being defined by that interface that you just put button, and now you have an extracted interface. And those extracted interfaces are almost always problematic and very, very likely to violate the risk of substitution principle. The problem is that the risk of substitution principle is often violated by attempts to remove features. And that sounds abstract unless we start thinking about what this actually means. So if we are to anthropomorphize a little bit, imagine that the read-only collection of T interface before would like to remove the features of iCollection of T. That would be very good if that was possible, because the read-only collection of T concrete class would like to implement the contains method and the copy-to method, because those methods are actually valuable and useful even in the context of a read-only collection of T. But the read-only collection of T would very much like to remove the add and clear and remove methods from my collection of T. It can't possibly correctly implement those methods. But the problem is that you can't remove methods from an interface in a specific derived class. So either you implement the interface entirely, or you don't implement the install. And then because we have this problem that the way that most languages and most platforms are designed, you can't remove features from an interface or other types, then you have to build this not supported substructure. And the more members you have on the interface, the more likely it becomes that there's one or more of those members that you'd like to remove. So the more members, the more likely it is that you have a bunch of these substructures. Now, it turns out that there's an interesting correspondence between the reuse abstraction principle that we talked about before and then the discussion of abstraction principle. So, if you comply with the reuse abstractions principle, it probably also indicates that you comply with the discussion of abstraction principle. The reason is that if you recall the reuse abstraction principle, they say that you should have more than one implementation of a given interface. So, if you've already demonstrated that a given interface can be implemented by multiple concrete classes, and you're already using those multiple concrete classes via that interface, you're already demonstrating that your system can work and can work directly with multiple concrete implementations. So it doesn't guarantee that you always adhere to the discussion principle, but it's a strong indication that you want to do. So you could also say that the reuse abstraction principle is used as a corollary to the discussion principle. Hopefully, this will be clear when we see examples. So let's look at the message store pass in the same read method and see how easy it is to accidentally violate the discuss substitution principle. At the moment, the only implementation of the store is the file store class that writes the text to the file system, reads the file from the file system in order to return the message associated with ID. Imagine that you want to change that strategy from using the file system into storing and reading the messages from the database like SQL Server. According to the close principle that we've learned about so far, the store is defined by the file store class. And this is not an abstract base class, it's a base class, because as you can tell, the members are virtual. So you can derive from file store in order to order behavior that you need to override. So in order to change behavior from using the file system and instead using a relational database like SQL Server, what you can do is, instead of having file store, you can create a new class that derives from file store, and you can call it SQL store. And you can tell that here I've overwritten the write all text and read all text methods in order to implement my database specific application. So I didn't write out the code here, pretty much. Here we have some standard database code sitting in the write all text and the read all text method. So that's fairly straightforward. But then we have a problem with the third method, the get file info method. And right here, just for the sake of example, I override the get file info method and then I just call it to the base implementation. So that actually corresponds to not overriding the get file info method at all, because that could just automatically then leave the base implementation. And I'm just doing it here to point out that there is this get file info method, and that turned out to be really problematic. So this is actually the method that violates the discourse substitution principle. But I'll explain exactly how that happens in detail. But before I do that, let's look at inheritance very quickly. So you have SQL store, which derives from file store. If you think that this is a strange inheritance file, you pull up this one. I think this is a very strange inheritance file. It seems strange that we have to derive from file store when we want to write a relation from the database. So we can go back to the file store class and have a look at it at the same time. So this is currently the only correct implementation of the file store class that we have. We also have this new SQL store class that I just derived, but it's not correct at the moment. It has problems with its get file info implementation, as we soon see. So instead of defining the abstraction as the file store base class, what we could try to do is to extract an interface from the file store class. So this is what I warned you about will probably lead to a violation of this substitution principle, and that's also exactly what happened here. So now I'm just going to do this anyway in order to explain to you why this is actually happening. So I'm taking those three members and I'm defining a new interface that I call iStore from those three members. So this is an extracted interface, and this interface actually violates the substitution principle, and I'll show you how it is. Now the only correct implementation that we have of this sort of abstraction so far has been the file store class. So we just need to go back to the message store class and change it from using the file store base class and instead change it to use the iStore interface instead. So that's just a trivial change. We can still, if we imagine that the file store class implements that new iStore interface, which is trivial to do because we extract the interface from the file store class, then we can still assign the file store class to store field because of it. So now we can go back to the SQL store implementation and say instead of deriving from file store, it'll just implement the iStore interface, which seems like a more sensible type hierarchy. And the write all text and the read all text methods are trivial to implement, so I'm not showing the implementation here, but that's basically just write it to the database or the database. It seems a little strange that there is the path involved here, but you can just use that string as a database key into the table where you want the messages and that is what you find all the strings without the necessary key. It seems strange, and we also later on return to not using a path but using something else with the write all text and read all text methods. But the real problem here with the implementation of iStore is the get file info method. Because as you tell at the moment, it throws multiple exception, because what else can we do? How can we return a file info that's associated with an ID when we're not using the file system to store the messages? We're using a database to store the messages now, so write all text writes to a database, and read all text reads from a database. Does it make sense at all to return a file info that's associated with an ID? It's not even mean in this context. It doesn't even mean anything. And we don't even know what to do about it, so we just throw it out. We really like to take away that feature, but we can't because then we couldn't implement the iStore interface because then it would apply. The problem is that throwing not supported exception layers is very, very problematic. So if we go back to the message store that consumes this interface, as you can tell, both in the same method and in the read method, one of the first things that happens, and that happens unconditionally, is that the get file method is being called. Now, if this throws not support exception, it means that both the save method and the read method will unconditionally also throw a not support exception. So this very strongly changes the correctness of the system, because before there was no exception being thrown at this point, and now the entire system is not usable at all because all the methods are going to throw exceptions unconditionally. So that's been our solution. Throwing not supported exception is not a solution in this case. So what else could you try to do? Well, you could try to change the implementation of get file info. So instead of throwing a not supported exception, maybe you could return some sort of fake or some sort of bogus file info instance here. Not something that's related to the entries in the database, but just some sort of fake file info that prevents the SQL store from doing exceptions. Would that work then? And this is where it becomes subtle, because if you look at the read method here, again realize that unconditionally calls get file info as one of the first things. And it uses the file and checks whether the file exists or not in order to decide what to do next. But keep in mind that if you have a database implementation of this interface, the file info that's returned from the get file info method is in no way related to the records you actually have from your tables in the database. So if you return a single bogus file info, the if statement that comes next will always evaluate true, either false or true, depending on whether or not the file that you return to get file info actually exists or not. So if you return a file that does not exist, it will mean that even if we have messages in your database that's associated with a particular ID, the read method will always be for the integration because it means the file doesn't exist. Or, on the other hand, if you return a file from the get file info method that actually does exist, it will always try to read that file and return a main region with the message that's associated with that ID, which may throw a different because sometimes the message does not have a different database. So this very much changes the way it exists, but it doesn't always throw exceptions. Particularly in the case where the file doesn't exist, it's just going to keep on returning and returning, even if you have data in the database. So this is the kind of subtle part that violations of the discontinuity leads to. And it's very problematic exactly because with the first implementation that you have of a given interface, you may not notice that you have this sort of relationship between these members and the interface. But then if you try and make a new implementation of that same interface, that's when the problems start to appear. And you may even not realize that when you create the same implementation, it's only when you start using the system that you realize, because bug reports come in, that you've chosen to version of the system, because it actually compiles, it just doesn't work the way it's intended to work. And in this case, what's actually happening is that you have an interaction between various members of the interface. So the get file info member is one member of the interface that we just extracted, and it interacts with other users of that interface, like when you have the text method. So the more interaction you have between various members of the interface, the more likely, and this was a principal violation, is to occur. And the more members you have on the interface, the more likely it is that there are some of those members that will interact depending on the implementation. So the fewer members with an interface, the more you reduce the risk of this sort of interaction occurring. So let's see what we can do about this. So going back to the file store. The file store class at the moment is the only correct implementation of iStore that we have in this system. So we also have the sequence store class that implements iStore, but it's not correct because we know that it throws this multiple exception or it has this problem with the get file info implementation. So we don't really have to take that into account if we want to refactor this, because it doesn't work at the moment. So it was never correct. The only correct implementation that we have of iStore at the moment, or the only implementation that works, is the file class. So let's see if we can do something about that, because what we really want to do is we want to remove the get file info method from the iStore interface, because it's impossible to correctly implement the iStore interface with, for example, a database, if we also have to implement the file info method. So we want to remove the get file info method. We want to remove the feature from the interface. And we can't remove the feature from the interface on the interface basis. So what we really need to do is to remove it from the definition of iStore altogether. But we need to do that in a way so that the message store orchestrating parent class still works. So we need to do this in the sense of store refactoring sense. So the first question you can ask here is that why does get file info method take a working directory's input? Somehow we should think that iStore class here already knows about which directory is the working directory. And that was actually what we had before, and somehow we lost that along the way. So let's see if we can get that back. If you recall how the file store looked like when we edit the module on the encapsulation, we actually have the working directory as part of the file store itself. And we lost this because we did a lot of refactoring, so we did two mechanical refactorings without even thinking about what we're doing. So even though you have a proper and a good refactoring tool in the IDE, it's not particularly against bad decisions like this. So let's see if we can get the working directory back as a part of the file store class itself. So first of all, we add constructor to the file store, and then we can add the working directory to the constructor, and then again define fields that will hold that working directory and add all the appropriate documents to that. So in this is just back to the place where we left off with the file store class back when we concluded the encapsulation module. Now we're just trying to get that back because we lost this through only a bit too mechanical interactions that I've been doing so far during the SOLID course. Now we're paying the price. So with the working directory field, we can now re-implement the getFileInfo method, not in terms of the working directory that's passed in as a method argument, but just in terms of the field that we already have passed. So if we're using the field of the class, there's really no need to have the working directory argument. And obviously it's defined by the iStore integration code. So if we remove the argument from the complete getFileInfo method, we also need to change the interface. Normally we don't get a complete class to find an interface, but that's actually what happened here because we extracted the iStore interface from the FileState class. So you can change the interface as well because the FileStore class that you just changed is the only correct interface that we can see. So this leaves us with a getFileInfo method defined on the iStore interface that does not take any interface. And if you look at this interface definition a bit, you might notice something else that's strange here. Because the getFileInfo method works on the level of an ID. An ID is a part of the main method. But then if you look at the write-all text and the read-all text methods, they don't work with an ID, they work with a path. So the interface is trying to model various concepts using two different levels of abstraction. And a given type should always work on the same level of abstraction. But right now, we're working on two different levels of abstraction. getFileInfo method is working on the level of abstraction where which is an ID, which is a much more abstract concept than a particular part. And then the write-all text and the read-all text methods work on the very concrete part. So what happens if in the write-all text method, we change the first argument from being a very concrete path to being an ID like this. Now if we do this, obviously we need to go back and re-implement the FileStore class so that it fits the new definition of FileStore. But that's trivial to do, as you can tell the write-all text method now it takes an ID as input, and the method itself then calls this getFileInfo to get the path, and then we can use that path to write the text to the file. But this is okay, even though we're trying to get rid of getFileInfo from the iStore interface. It's okay and safe to call the getFileInfo method from within the FileStore class, because in the FileStore class, getFileInfo is a concrete method. It's not part of the interface necessarily, and it will be available in the concrete FileStore class even if it wasn't part of the interface. So that's fine, we can do this. Now if we do this, we also have to change the save method in the listStore class. And you can tell now that I've changed the getFileInfo method call so that it should pass in the working directory and it also just pass in the ID. But then if you look at the current usage, nowhere is that file actually used. Because I also changed the write-all text method so that instead of relying on the path, it actually just relies on the ID. So the file that's being generated by a call to FileInfo is never being used with the save method. The file variable can be used. So you can safely delete that method all the time. So that removes the need for having the getFileInfo method when viewed from the perspective of the save method. But the getFileInfo method is being used also by the read method. So we're not quite out of the woods yet. So let's look at the read-all text method. It takes a concrete path as the single input argument at the moment. And that's still a different level of abstraction compared to the ID arguments that the two other methods take. So let's change the read-all text argument from path to ID as well. And now, while we are still at it here, we might as well just take a cue from the way that we defined the original FileStore back when the argument was created and say, instead of just returning a string, it really ought to return a maybe of string. And there are reasons why I do this, but this actually turns out to be a very good idea. So if you go back to the consumer of this type, the read method, let's see if this actually helps. And it turned out, at the moment here, we got rid of having to use the working directory, but the file is still being used. So in the same bit, the file ended up not being used at all. But here, the read method actually uses this if not file exists, then blah blah, and otherwise something else. And that turns out to be automatic. Particularly, one change that I have to make in this read method at the moment is that I have to add .single after the call to the old text. So you can see here that when the cache is being invoked, it says this cache get or add and it passes in the ID, and then it passes in this delegate, and the delegate is being invoked if it turns out that the cache value does not have an element in the ID. When it calls this sort of read all text. And I just change read all text to return a negative string. And the problem is that get or add expects a delegate that returns not a negative string, but just a string. And in order to make it all compile, I have to invoke .single in order to return a string, that's the negative string. And right now, this is almost safe in the sense that we know from that check of if our file exists that if we reach that part of the read method, if we have already exited because the file doesn't exist, it's safe to call .single on the return value of the old text, as long as the implementation of the store is file store. So it's safe at the moment because the only correct implementation of store that we have is file store. But now this code is relying on implementation details. It's relying on the knowledge that if this .store is a file store, then the backing file is the file that returns from the default file into a literal. And then if the file actually exists, it's only simple. But this would break left and right if we ever get to the point where we can replace the file store with something else. So that's really problematic. So let's try to understand why do we have to call .single after the text. So in order to understand this, we have to go back and look at the cache implementation. So here's the store cache, and we get or as method expects to pass in an ID and then a func of a string. And the point here is that we're just calling into this cache of get or add, so that's just the way that the dictionary looks like. So the idea is that we are getting the message associated with the ID, but then if the current dictionary does not have an entry for that ID, it will invoke the list factory to produce the message, and then it will add the message to the current dictionary that will return. And right now the dictionary is defined as the current dictionary of int and string, so we can't add a maybe of string to this current dictionary. We have to add a string, and that's why we consume code here just before have to call .single on the read all text return value. Now, if we haven't learned anything yet, we can extrapolate the interface from the class we just looked at and call it high store cache, and then we can have that interface to the store cache of the class that we call. And you can just imagine that as I'm refactoring along the way, I'll also be changing that high store cache interface. But that high store cache interface is also an extracted interface, and it turns out that's not the final interface that we actually use. So if we want to get rid of that call to .single or in the message store into the code, maybe we can change the get or add method so that it fits the actual return type of the text method. So instead of defining in func of int and string, maybe if we redefine it as in func of int and maybe of string, things would be better. So as viewed from the consuming side, you no longer have .single, but the problem is that now you're just doing the problem inside of the store cache implementation here, because now I can no longer just pass in the message factory, but I'm actually having to provide a new delegate that takes the index and then calls the message factory and then calls .single. And at least before, at the consuming side, I knew that if there was a check whether or not the file existed, it was sort of safe to call .single at that point. But here we do not have that information at all, so we don't really know whether calling .single on maybe is safe, because the maybe that we return from the message factory might actually be an empty maybe, in which case the .single method would go exception. And now we are still breaking the discussion. But the thing is, this actually puts us a little bit closer to the solution, because the current dictionary that we have here at the moment is just an implementation detail. Right now it's defined as a current dictionary and a string. It doesn't have to be. So let's see if we can start by changing. What if we change the get or add method definition? So instead of returning a string, it will return perhaps a maybe string. And if we do that and at the same time also change the concurrent dictionary, so that it's no longer going to be a concurrent dictionary of each string, but a concurrent dictionary of each maybe a string, then all the pieces of the puzzle fall together again. So now we have a concurrent dictionary of int and maybe a string. And if you look at the get or add method, it takes a func of int and maybe a string just like before, but I can just pass this business factor directly into the get or add method from the concurrent dictionary itself, and it's going to return this string. So if you go back to the message stored in the dictionary and look at what does it look like now, you will notice that we no longer have to call that simple after the text. Read on text returns a maybe a string, and that's also what we get or add method in the cached space. So we still have the call to get file information. We need to do two different things depending on whether or not the file exists. Actually, what we care about is not so much whether the file exists or not, but rather whether the message exists or not. So now we can take a get file info code and the associated code that checks whether the file exists. It doesn't belong at this abstraction level. You can move that into the file store where it belongs. So now we're pretty much back at what the file must look like when we left it and the function of the encapsulation module. And we lost all of this along the way because we did refactor it without thinking, and we probably should have applied thinking while doing refactors. But now we're pretty much back at the beginning. So if this is the implementation of iStore has changed as I've shown you along the way, then the consuming part now looks like this. So we no longer have to have this call to this install of get file info in the read method, and instead it can just call just a cache of get or add, and the delegate inside that is this control of read on text. And what that's going to turn is a maybe a string. And then we test if message is any, then we can lock that we can return the value or otherwise we can return the find the message for the child. So the save method and the read method now no longer depends on the get file info method on the iStore interface. But as you can tell, the last of the three methods that we have get file info outer message still falls into this install get file info. That still depends on iStore and get file info, but at least we've been able to move in the right direction. But let's look at the SQL store implementation now. So the SQL store implementation is still like we left it as before. The write all text and the read all text methods are implemented using the database, and then we're very much supporting the get file info method. But at least it turns out that we're only using the get file info method from other get file info methods, and we're no longer using the get file info method from the same or the read method. So at least we're not changing the parameters of the read method. Now we could actually use the SQL store class with the same and with the read method without choosing the system. So all we did now is to also get rid of the dependency on iStore and get file info from the outer get file info method there in the document. And it turns out that part of the solution to how we eventually get rid of this method from this interface is related to the interface definition. So I'm just going to leave the code here. We're not completely done with refactoring. We're not really correct yet, but we are on the right track. But before I show you how to get rid of iStore and file info and arrive at a good design that does adhere to the list of substitution principle, I'll stop talking about the list of substitution principle now, and I'll talk about something else for a while, and then later on I'll show you when I talk about the simplification principle how to finally resolve the situation. So far we've covered the single responsibility principle and the open closed principle of the pluralsight principle. Now it's time to look at the list of substitution principle. So when we talk about the open closed principle, we talk about extensibility. And we only talk about extensibility in terms of concurrence. But I also told you that you should favor composition over inheritance. And the list of substitution principle talks about polymorphism, and that's an important aspect of understanding how to go about composition. So the reason it's called Liskov substitution principle is because it's named after Barbara Liskov, who originally back in the 70s described this principle. And she described it in very mathematical terms. So if you read the original paper by Barbara Liskov, it's mostly in Greek letters. And I admit that I have myself tried to skim that paper, but didn't really understand what it was trying to tell me. That's probably a very common feeling if you're trying to read the original paper. So Robert C. Martin tried to make this a little bit more understandable for us by saying subtypes. Hello, my name is Mark Seaman, and this is module 6 of the Encapsulation and SOLID pluralsight course. So in the previous modules, you learned about the equal responsibility principle and the open close principle, and the Liskov substitution principle. But before we continue on and I'll teach you about the Encapsulation principle, I'd like to stop and just reflect on what we've done so far. So let's start with a story. A couple of years ago, my son came to me with his hands full of glucose, and he asked me, Dad, when did you supposed to be a dragon? I think he was 3 years old at the time, so when you're 3 years old, you don't have very long hands, and glucose actually are pretty big, so a handful of glucose just amounts to 4 kilos. So I looked at those 4 glucose and I thought, how am I going to put the dragon like this? So I looked at it a little bit, and then I put the bricks together, and I did it like this. And I was his father, and he was 3 years old, so he was actually quite happy with the result. But if I just show you this constellation of bricks to you and ask you, what do you think it is, you probably would not identify it as a dragon. Maybe you'd tell me it's a cow, or it's a dog, or maybe say it's an airplane, or a racing car. You probably wouldn't recognize it as a dragon. And this got me thinking, what's the problem here? The problem is not that Google is not a building system, the problem is one of granularity. So if you take the same amount of plastic, or the same volume of plastic, and convert it into Lego, so Google, so each Lego brick amounts to 8 of those 2x4 standard Lego bricks. So this is the same amount of Lego as in the previous sample, which is the Legos in Google. So if you want to build a dragon out of these blocks, you can do something like this. Now granted, this does not really ask us for special efforts, but at least it's recognizable as a dragon. And actually, to prove that that was the case, after I built this dragon, and after the picture, I just left the dragon here on the floor and waited until my family came home, because I was home alone when I made this. And my wife came into me and took me along with the dragon. And my son came with dragon and said, Dad, you gave me a dragon. And I had to ask them whether they could identify what that was. They just immediately recognized this as a dragon. So the same volume of Lego went into building this dragon that went into building the Duplo dragon. But this is just much more recognizable because the granularity is smaller. And you probably know this from digital imagery or anything else. The better the granularity, the more it looks like the more thing. So this should not surprise you at all, but it also applies to software. One of the problems with SOLID when people encounter it is that when you apply the simple responsibility principle, and when you start to apply the open close principle and this whole append-only strategy that I talked about before, you end up having lots of small classes. And I mean lots of small classes, like hundreds of classes. And many programmers, when they see this for the first time, really accurate problems, but they're really scared of code structures like this because they just look at the file structure or the solution explorer in the IDE, and they just see that there are so many classes there, so many types, and that looks very complicated. And they ask me, how do you navigate this like this? But really, that's not more code, you just arrange the code in a different way. The problem is that we humans suffer from something called unit bias. And unit bias is a cognitive bias. It's not particularly related to software development, but we software developers are humans, anyway, so we suffer from unit bias as well. So here you actually see the illustration that a single Duplo brick is the same size as a normal standard label is, but the label is just smaller, so that's why this bias is a universal cognitive bias. It doesn't apply to software development. It applies to all sorts of our daily lives. We just tend to see a unit of something as being a unit of something, and we don't really take into account whether that unit is actually small. Studies have been made that demonstrate that if you give people a plate of food, most people will eat the food. And if you give them a big plate, they will still eat the plate of food. And if you give them a smaller plate, they will still eat the plate of food. They will feel like they've done more in cases. So if you also lose weight, then use a smaller plate. Or if you need to gain weight, then use a big plate. The unit bias is a universal cognitive bias that we humans suffer from. But we also suffer from it when we work with software. So having a code structure that contains hundreds of classes seems scary. But actually, I have plenty of code bases that have hundreds of classes in the namespace. And when other people see that, they seem to be a little scared of it. And they ask me, how can I actually navigate in that code base? And then I show them that each of those classes are so small that they tend to fit on a single screen, even on my laptop computer. So it's very easy to reason out each of those classes. And if the abstraction level is also, you don't really have to understand the implementation details of each of those hundreds of classes. So you can ask yourself, what do you really prefer? Do you prefer hundreds of classes where each class is trivially simple and fits on a single screen? Or would you rather have 10 classes where each class has thousands of lines of code? And I know that I prefer the hundreds of classes that are all very small because it's a better level of granularity and enables me to compose all of those classes to fit the picture that I'm trying to build. And that's much harder if you have few big classes because then you have to do those dragons all over the place. It's time to look at the interface integration. The interface integration principle will help you solve the problems with this execution code violation previously solved. So this is a good example of how the 5 SOLID principles enhance and interact with each other. Basically, the interface integration principle states that clients should not be forced to use content they do not use. And that raises another interesting question. Who owns the interfaces? Who defines the interfaces? Most programs have a tendency to think about interfaces in terms of the concrete classes that we create with interfaces. But the reason why interfaces exist in the first place is to structure. And it's not really the concrete class that we see as it's the client that needs the interface. So the client owns the interface. The client defines what it needs. And there's no reason for the client to define the member of the interface. So it's important to realize that you need to think about interfaces in a different way than most people think about interfaces. Interfaces are not defined by the concrete class that interface the interface, but it's defined by the client that consumes the interface. And since the client defines an interface and it only needs to define what it needs, there's no reason to have big interfaces. So you should favor low interfaces with big interfaces. So what's a header interface? You've already seen a header interface. That's those extracted interfaces that you've already seen. That's the interface that's extracted from a concrete class and has lots of members. And the reason why we call them header interfaces is because they almost look like old-fashioned header files. Like, for example, if you ever lived in sort of cluster, you will know that first you have to define a header interface that contains declarations of all the methods that the class will have, and then in the CP file itself you have to repeat all of those members, and then you provide the implementation in the CP file itself. So the header file is sort of redundancy, and it defines which parts of the C++ class that's actually supported. But nowadays we have other language constructions that really just do that in a less redundant way. But a header interface looks like a file in the sense that it mainly just states these are all the methods that are available on that concrete class. And it's very unlikely that if you have a big header interface that you will ever be able to use another concrete class that implements the same interface without doing lots of massive work from there. So those are header interfaces, those are those extracted interfaces. They may not be a header interfaces, which is those big interfaces. On the other end of the spectrum, we have something called a role interface. The role interface is an interface that defines very few members. And again, if the client gets to define what an interface looks like, it will only need to define exactly the members that it needs to talk to. And the extreme role interface is an interface with only a single member. And those are the types of interfaces that I tend to define at the time, because it turns out that if you define role interfaces with only a single member, you can actually much easier resolve problems with the discourse substitution. For example, if you think about the example that we looked at when we looked at the discourse substitution principle, you look at this I-store interface. And that's an interface with only 3 members. So even if it only has 3 members, it still has a problem with the discourse substitution principle, because there is an interaction between several of the members in that interface. So even though you probably think that 3 members is a small amount of members, it's still enough to be problem with the discourse substitution principle. But if you have an interface with only a single member in that interface, there can be no interaction between members of that interface, because there are no other members on that interface that that single member can interact with. And that very effectively protects you from a big category of potential discourse substitution violations. So the bottom line is that in this case, substitution principle can be solved issues with the substitution principle. And this comes back to this whole discussion that I already touched upon before with adding and removing features from the codebase. In most mainstream programming languages, it's not that hard to add features. And we have all sorts of ways in which we can extend existing code. We can derive from the base class, implement the interface, we can add new classes, we can add generic arguments to a method or a class that's not already generic, and so on and so on. So it's not particularly difficult to extend existing code. And we all work here from the word extension itself, and extensibility, and extent means to make something bigger, not making it bigger. So we have lots of ways where our languages enable us to add features, but not a lot of ways in which we can subtract features. It's actually not really possible in most languages to subtract features from accessibility. But the good thing about the interpretation principle is that it helps to solve problems with removing features, because it defines features in such a granular way that if you don't want to have a feature, you just don't implement the interface. And I'll show you an example. Here is the SQL store class as we left it in the previous module. So it still implements iStore, and it still throws not supported exception from the get file info method. So that's what we need to resolve, and we can now resolve this problem by applying the interface substitution principle. So before, we extracted the iStore interface from the FileSort class. But that means that since we extracted the interface from the country class, what we really defined was iStore as the interface. Instead, we should let the client define the interface. So where is the get file info used? Well, it's being used over a message store in the bottom of these 3 methods. In the file info outer method, it's called method store of get file info, and store is an instance of iStore. So this is the only place where iStore does get file info called. So instead of extracting the interface from a class, we could extract the interface, or we could let the client define the interface. In this case, let the client define that it needs the get file info method, and we can define an interface with that simple method. We can call that interface IFileLocator. And as you will notice, that IFileLocator interface only has a single method. So that's as small as an interface can be and still be useful. So technically it's possible to define an interface that doesn't have members at all, and we call it a marker interface. They tend to have limited use. There are some special cases where it is useful, but in general, marker interfaces are really interesting. So an interface with a single member is the extreme role interface. It actually does provide some behavior that some client actually needs, but not any more than absolutely strictly necessary. So if we go back to the client and look at the save and the get file info methods, we'll notice that only the get file info method relies on iStore as the file info. And it's quite interesting to see, by the way, that if I highlight the usage of store in each of these three methods, the save method uses the write all text method, the read method uses the read all text method, and the get file info method uses the iStore get file info method. So each of these three methods use different methods on iStore. The save, for example, doesn't use read all text or get file info, and the read method doesn't use write all text or get file info, and so on. So right now, all of these three methods violate the interface principle because they all rely on the iStore interface, but they also depend on methods that they don't use. But now in the get file info method down at the bottom here, there's no reason to rely on iStore because the only thing the get file info outer method here needs is get file info method. And now we've defined a new role interface that also defines the get file info method. And that's all that the get file info outer method here actually needs to rely on. So instead of depending on iStore, we might as well just change this to depend on file looking method. And you'll notice that I also changed the access here, so instead of saying this.store, now it says file locator. And you can imagine that what actually happened was that I also added a file locator virtual property, just like this class also already has the log virtual property, and the store virtual property, cache virtual property. So the list of those virtual properties, those factory properties that sits beneath us at the moment here, that list grows, and that turns out to be a problem in itself, but before the course is over, I'll show you how to get rid of all those virtual properties. So it's not going to be a problem here, but right now I added just another one of those. In this system, these three methods are the only clients of the iStore interface, and now no client relies on the iStore get file info method. So we might as well just do this method and nothing will be great. And then again, here you can go back to the single store class and implement iStore without having to deal with the get file info method. So now we've arrived at a solution where we define iStore as a way that the list substitution principle is no longer violated. And it's possible to replace file store with SQL store, and the message store class will still continue working as it's supposed to, and now we just have messages SQL server instead of the class. That was interesting. So by applying the interface simplification principle, we could resolve some pretty serious problems that we had that violated the risk of substitution principle. So at the moment, the risk of substitution principle that we know of hasn't been solved, but we may have other problems with this, but we don't know of yet, that we haven't discovered them here at the later level. So what happens if we take the interface simplification principle and apply it to the rest of the principle? Because we still have get interfaces left. So what if we go through the entire code base and systematically eliminate all the header interfaces and instead introduce appropriate role interfaces? It turns out to be a really good idea. So let's do that. So here's the message store class, and I've taken down the get file info method because it's not particularly interesting anymore, just force it to just define the get file info. But we still have the save method and the read method, and it's not that they did particular properties, but still we might be able to use some interesting with those methods. And let's start with the save method because that's actually the easiest one to factor. So a while ago you learned that abstractions are not designed, they are discovered. And they're discovered by looking for commonalities in code. And again, right now we learn about the interface simplification principle and how the client gets to define what the interface looks like. So if you look at the save method here is a client. What does the save method mean? And what are the commonalities? If you look at those four methods, the log and save method, store and write all text, cache method, log and save method, what do they have in common? Can you tell what they have in common? Well, they don't have the same name, but is there something else that they have in common? When I ask audiences these questions, they soon realize that all of those four methods takes ID as a parameter. So that's one commonality. We have methods that take ID as a parameter. What about the return type? Are those methods commands or queries? Well, these are all commands. All four methods return void. So we have four different commands that all takes an ID. Is there any other commonality we can identify between these methods? Well, the last one is not quite as apparent, but two of the methods take a message as an additional argument, and the other two methods do not. Now, the outer save method takes the message as an input argument into the save method. So we can always pass the message string onto whichever method will be called from within the save method. And again, keep in mind that the save method is defined, so that's the client that gets to define what the interface is going to look like. It wouldn't be far off to say if the save method gets to define what log.saving looks like and log.save looks like, it could pass on the message to the as well. So let's look at the log here. Here's another extracted interface. It's one of the header interfaces that we don't like. But still, can we do anything about it? Let's start by just looking at what we have to work with here. Say, what if we added that message to the saving and saved methods? Now, that wouldn't really be a problem because the only consumer that we have at the moment of iStore.logger, the only client that we have of iStore.logger is the save method that we just looked at. And it can always supply the message. On the other hand, any concrete implementation that we had before that implemented iStore.logger didn't take the message. So now if we predefine iStore.logger that we take the message in those two methods, the concrete class can just choose to ignore those messages it didn't use before, and it can just keep on not using the message even though it's passed in. So we're not really breaking anything at the moment. This is okay, we can do this. So going back to the save method here in the message store class, let's look at how common we things like now. And we still have four different methods. They all take an ID message, but they have different names. Let's start by just looking at one of them. So let's look at the iStore interface. So the iStore interface here is still a header interface because it's an interface that we extracted from a concrete class. So even though it only has two members, it's still an extracted interface. And this is also another good example of how extracted interfaces may not actually help you a lot, because it turns out that those extracted interfaces have a lot of things in common, but it's difficult to actually see what they have in common because there's too much noise about them. One of the things that I often do when I start to look for some analysis is to not really care about the names. So names are more or less like noise when you're looking for common abstractions. So there's no particular technical reason why the write-all-text method is called write-all-text. It's just a residual of the fact that this interface was extracted from a concrete class that had the method with that name. But technically, it might just have a different name. It might, for example, just be called save. And we can do the same with other extracted interfaces as well. So here's the iStore cache interface, and there's again no reason why the add or update method has to be called update. So might as well just be called save. Now, if we go back here now, we can see that we have two methods that are called save, but then we have two other methods called log.saving and log.save. And we can't rename both of those methods to save because both of those methods are defined on the same interface, and we can't rename two methods on the same interface to the same name. That's not going to be possible. But still, it looks like we are very close to arriving at something that is common abstraction. So we just need to figure out what to do about this. So we can even highlight all this stuff. And one thing that's also interesting to notice is that not only do we have something that has the same structure, the same method signature as each other, it also has the same method signature as the overall client method, the same method itself. So this is a very strong indication that there is an abstraction that's screaming at us that wants to come out, and we just haven't really seen it yet. So again, we can let the client define the interface, and we can define the iStore writer role interface that only defines a single save method. And the save method that we looked at before, the outer save method that we looked at before, can call this interface because that's all it needs to invoke. we're still having the problem with this.log.saving and this.log.save, because we can't have two different implementations of the same interface in the class. So we need to resolve that problem before we can finally use the same abstraction for what we do. So what you can do to solve this is a little trick that you'll probably not like, and you would be right to not like it because I don't particularly like it either. But it's just an intermediate step to show you the steps that you can go through. And when you're done with the refactoring, the classes that you probably not like is going to go away again. But what you can do is, instead of having a big store of a class that implements various interfaces, you can define a very small class that implements iStore driver. So log saving store driver implements iStore driver, and the only thing it does is just logging the information, saving message. And you can probably guess what comes next. Apart from this log saving store driver, you can also add a log save store driver. And it's almost the same class, it's almost the same implementation. There's just two characters in difference, because it's now not logging saving message, but it's logging saved message. But that's the only way. And that is a very, very small class that implements the lower interface. And if you think this is just too much of a micro class, I can understand why you think that, but that's not the problem that I have with these micro classes. My problem is different. So my problem is that in order to use these two new classes, I have to move them up in order to use the same department. But it looks very nice that you can very much see the similarities in those four calls to different save methods. So it looks like you'd be able to replace this with just four calls to the same save method on the same interface. But we're having this problem with having to new up a new log saving store writer and a new log save store writer. So this is just in line with the more traditionally. The problem here is that now in my eagerness to find common construction, I've violated the close principle, because now I can no longer change my mind about how the log saving store writer and log save store writers are implemented, because these are being used up inside the same class itself. And I could create virtual properties that define a log saving store writer and a log save store writer if I wanted to do that. And that creates an explosion of all of those factory properties that sits in this particular message store class, and it just gets worse and worse and worse. So that also demonstrates why a factory level and inheritance in general is not a good extensibility mechanism. It's possible to address this problem with composition, and I'll show you how to do that in the next module. But for now, I'll just leave this as a cliffhanger, and then in the next module, I'll show you how to do this. Hello, my name is Mark Seaman, and this is module 6 of the Encapsulation and SOLID pluralsight course. So in the previous modules, you learned about the sequence 1 principle and the total post principle and the substitution principle. But before we continue on, I'll see. Hello, my name is Mark Seaman, and this is module 7 of the Encapsulation and SOLID pluralsight course. In this module, you'll learn about the dependency inversion principle, but before we start talking about the dependency inversion principle, I just want to share with you a brain teaser, if you will. So that's the story about the master and the novice. So the venerable master Kna was walking with his student Anton. Hoping to prompt the master into discussion, Anton said, "Master, I have heard that optics are a very good thing. Is this true?" Kna looked pityingly at the student and replied, "Foolish pupil, objects are merely a poor man's closures." Chastised, Anton took his leave from class and returned to his cell, intent on studying closures. He carefully read the entire, laughed at the ultimate series of papers and its cousins, and implemented a small scheme interpreter with a closure-based object system. He learned much, and looked forward to informing his master of his progress. On this next walk with Kaplan, Anton attempted to Mrs. Master by saying, Master, I have diligently studied the matter, and now understand that objects are truly a poor man's closures. Kaplan responded by hitting Anton with the stick, saying, When will you learn? Closures are poor man's objects. And at that moment, Anton became enlightened. Now, this is a lovely parable, and I didn't come up with it myself. Anton's garden has that distinction. But it's a nice story in the sense that it illustrates very clearly that objects and closures are very closely related to each other. Let's try to understand what that actually means. So if you don't know what a closure is, then don't worry, I'll get that in a moment. So to follow SOLID to one of its extreme conclusions, you arrive at quite an interesting place. So we already know that if you apply the single responsibility principle, you end up with lots of small classes. And also, if you apply the interface simplification principle and use the extreme version of a role interface that only has a single method, you might end up with a system where you have lots of high-grade classes with a single method. Now, you probably learned that objects are data with behavior, and this is an excellent definition of what an object is. It's behavior. I buy totally into that. No problem with that definition at all. So let's look at what an object is. Data with behavior. So here's a file-store class. It's not quite the same file-store as you've seen so far. So you can imagine this is a file-store class from an ultimate universe. It looks very much like the file-store classes we've already seen, but it's a bit simpler. It implements an interface called iMessagery, and this code actually compiles, so since the class only has a single method, you can infer that iMessageQuery also is an interface that defines the single method. It defines the read method. So the read method takes an integer as input and returns a string, and the integer is an ID, so somehow the read method returns a message that's associated with that ID, just like we'd seen it before. But the file-store class also has data because it has this working direction, and that's data about the object. The read method does what it usually does. It does path combined with the working directory and the ID, and then int.txt, and then it calls file read all text with that path and returns the contents of the file, like before. So the read method is the behavior of the object, and the working directory is the data of the object. So an object is data with behavior. That needs to fit in this particular case. Okay, that's a nice object. So what about functions then? Now functions are defined as pure behavior. It's only behavior, there's no data captured by the function. So what would that look like if we want to write a function that does the same thing as we just saw an object with? So I'm not going to try to show you a function language yet anyway. So this is sharp code. So we can write functions in C# as well because we have these derivatives. So this is a function of directory info int and string, and we can call this function read. And what it does is it takes working directory and ID as input, and then it defines a code block that does exactly the same thing as the object we saw before. It calls the path combined with the working directory and the ID, and then it calls file that read all text with that path, and then it returns the contents of that file. Just like before. But it's not an object, because there's no state, there's no data being clicked by this function. You have to supply all the values as input arguments in this function in order to use it. So it doesn't look like an object. It's also not a closure. So for functional programming, we have this concept of closure. And in C#, a closure might look like this. So what you do is that outside of the function, you can define value. In this case, we call the value working directory. And we can work directory value in a particular instance of the directory. And then you can define the function as a function of int and string. And you can still call up the read. And it takes the integer as an ID as input, and then it has the same block as before. So it calls path to combine on working directory and the ID and print.txt, and passes the path to file the read all text and returns the result of the read all text. Now the difference here is that this function closes over the working directory. The working directory is called an outer variable. So since it closes over the outer variable, you can say that it captures the outer variable. This is a closure. And what does that compare to? This was sharp code. if you look at what it compiles to, it compiles to something like this. Or actually, it compiles to IL code. Then if you back compile it into C# code again, it looks something like this. So it looks a little bit strange, but it's a class. The class has a strange name, but it is a class. And this class has data. It has working directory, which is a directory info. So it's not a private read-only field, it's actually a public field, but its data is pretty much the same form. It's just some technicalities that makes it different. And not only does it have data, it also has behavior because it has a method. And this method is a really strange name because it has angle brackets around it and all sorts of things. But it's a method that takes an integer called ITS input. And then the implementation of that method is the same thing as before. It combines the working directory with the INET test.txt and passes that path to file.read_text and returns the result of the new file, just as before. So it looks like the original object, but this is not an object. This is not basically behavior. We started out by defining this as behavior with data. So closures are behavior with data. It pretty much just depends on your perspective. So what's more likely? Here's the original object that we built. It's nice. And here's the closure. Now the nice thing about the closure is that you don't have to come up with a name for the concrete class. You don't have to come up with a name for the interface. So you just have to come up with a name for the function. So in that case, it's a little more likely. So there are various aspects of C# that makes this a bit difficult to work with. But if you actually do this in a functional language like C#, that has all the right language constructs in order to make this thing work well, then you get something that's even more likely. So the interesting thing is not that we're going to spend more time on functional coding now, but the interesting thing is that if you follow the SOLID principles to some of its logical conclusions, you end up with some object-oriented code that's not too far from being functional, or it could easily become functional code. So if you're interested in more about this, you could watch my other pluralsight course called the Functional Architecture with F#. But for now, we'll just move this on and move on to the last SOLID principle. It's time to look at the last of the 5 SOLID principles, the dependency injection principle, which states that high-level modules should not depend on low-level modules. Both should depend on abstractions. Also, abstractions should not depend on details. Details should depend on abstractions. So this is closely related to the specification principle in the sense that clients own the interfaces. So a client can talk to an abstraction because it owns the interface. And whatever is on the other side of that abstraction is an implementation. Now that we talk about the dependency injection principle, we can also finally start to look at composition and how to favor composition with inheritance. But before I start to talk about that, I think it's important to state that the reason why we now know that inheritance is problematic is because all the mainstream languages that support inheritance these days only allow simple inheritance. And that means if you derive a class from another class, you immediately close off all other options you have from deriving something else. So in other words, deriving from a class puts a very big restriction on the derived class, because now it can never derive from any other class. And that makes the derived class very flexible. So instead of all that inflexibility, you can use interfaces to composition. And everything you do with inheritance, you can also do with composition. So there's nothing lost in favoring composition of inheritance. But still, if you have a language that supports multiple inheritance, the overall knowledge we have today that inheritance is problematic may not apply to that language. So back in the 80s, when Bertrand Meyer talked about object orientation, he talked about inheritance all the time. But he also talked about a language called IFO, which he had invented himself, that supports multiple inheritance. So it didn't have any interface specifically. So that's just a little caveat on this favorite position of inheritance. But if you're working with Java or C# or other mainstream object-oriented languages these days, they only support simple inheritance, and that means that you should favor inheritance. In the rest of this module, I'll show you two different ways to perform composition. The first one is by using a design pattern called composite. And this is one of the design patterns originally described in the book Design Patterns from 1994. Here's the problematic save method as we left it in the previous module. So we're still looking for a common abstraction in order to perform the four actions that we want to perform as part of the save method here. But the problem is that right now we are violating the compose principle. So what we're looking for is an implementation that does not violate the compose principle, but still allows us to use this common abstraction that we just defined, this iStore interface. So a composite is just a very special implementation of an interface. In this case, a very special implementation of the iStore interface. And a composite might look like this. There's a class that implements iStore Rider, but it also contains an arbitrary number of other iStore Rider implementations. And there are various ways you can implement a composite in order to populate with those other iStore Riders. But in this case, I just like to pass in a parenthesis array to the constructor and just assign that array to the composed array of iStore Riders that this composite composes. And since the composite store rider also implements the iStore Rider itself, it has to implement the save method. And what it does is it simply just loops through all the riders that it composes, and for each rider that it composes, it calls that rider's save method, passing in the ID and lists that it got from the outside. And notice that it passes in the same arguments that it got from the outside, and it loops through the riders in a determinist order. And it loops through all the riders until there are no more riders. And if there's no exception thrown here, the save method returns, and it guarantees now that it's called all the riders save method in the correct order. So if you have such a composite, it becomes much easier to deal with the problem just at hand. So instead of having the detailed steps here, where we both try to create some of the classes and then call the methods on them, what we could do is instead is just this.rider.save. So we haven't seen the property called this.rider yet. This is a property that I've just added for this particular purpose. And it's one of those factory properties, in this case a factory property that returns an instance of iStore Rider. So how do we compose this? Well, let's look at the constructor of the list.store class. So you can see here there's some highlighted code, and the highlighted code assigns an object to this.rider. And here you notice that this.rider in this case is a lowercase w, where in the same that I'm calling this.rider with another case w. So again, I'm assigning a default field here. I can always override this using one of the factory methods, and then right here, that's what we use to mark. I'll get rid of this later on. Notice that the rider field and the rider penalty are defined as iStore Rider. So it's not defined as composite store rider, but since composite store rider implements iStore Rider, it's possible to create an instance of composite store rider and assign it to the iStore Rider field. And in this case, the way that the constructor creates an instance of the composite store rider is that it says, first it creates a new instance of log saving store rider. And then it passes in the file store that it already has created just a couple of lines above. And file store implements iStore Rider already. And it also passes in the variable C, which is an instance of the store cache, another class that implements iStore Rider. And then finally it creates a new instance of the log save store rider, which also implements iStore Rider, and that's the final instance that it passes to the composite. So when the save method just down below calls this.rider save, it actually calls the composite store rider save method. And the composite guarantees that it's going to loop through all the composed riders and call their save method in the correct order. So this is just the same as before. But what really happened here is that we've decoupled the method call from how the object graph is being composed. And that means that you can now derive from this store if you want to do that, and then you can override that rider factory property, and then you can redefine how you compose the composite store rider. So if you want different loggers or different caches and so on, you can compose those into a different composite. The composite sign pattern works very well with commands. So you just saw how the composite design pattern can be applied to the save method. And the save method is a command because it returns void. And composites work very well in combination with commands because you can compose as many commands as you will, and you don't have to worry about the return value because there is no return value. Now, if you want to compose queries, the composite design pattern is not quite as well suited because now you have to deal with the return type of various methods. It's not impossible, but it becomes more difficult to use a composite when you deal with queries. So there's another design pattern called decorator. The decorator is very well suited to compose queries, and actually it's also very well suited to compose commands as well. So if we go back to the code that you already have, I'll just show you how to refactor the save method first, and then afterwards we can look at the read method. But this will just show you how the decorator design pattern can be used both for commands and for queries. So a decorator is almost like a composite in the sense that it's a class that implements an interface. In this case, for example, let's look at the store cache. This is not a decorator yet, but it will be in a moment. Store cache already implements iStoreWriter. So that's the role interface that defines the save method. And you can see the save method here in the middle of the screen. So that's why it implements iStoreWriter and automatically compiles. So if you want to turn the store cache class into a decorator, not only must it implement iStoreWriter, but it must also compose iStoreWriter. And the way you can do that is by adding an iStoreWriter to the constructor and just assign it to a field, just like you said before. You probably also should add a guard box here, but I'm not going to do that because it takes up space and it's not particularly important in this discussion. Now you have an iStoreWriter that you compose, and you also implement iStoreWriter in that store cache class. So in save method, what you can now do is you can call that inner writer, that writer field, and call save on field. And that's the first thing you do. And then after you call writer.save, you can then go ahead and do whatever you want to do in order to cache the message, just like before. And if you squint, you could almost imagine that instead of saying this.writer.save in the first line of the save method, you can almost imagine that it says base.save. It would amount to the same thing if store cache, instead of composing iStoreWriter, if it derived from something that defines the save method, that would always be the same. So now it says this.write.save instead of this.base.save, but it plays the exact same role. It solves the same sort of problem. So this is a great example of how can you replace inheritance with transition. And it turns out to be much more flexible because you can decorate more than one interface while you can't provide for more than one base class. Another thing that's interesting about the save method of the store cache class here is that it starts out by calling this.writer.save, so it calls the inner writer, and then it does whatever else it needs to do. So that's where it adds value, that's where it adds its own behavior. Now that we have the store cache as a decorator of iStoreWriter, we can go back to the save method and look at the implementation. So the implementation of the save method is the same because this.writer is still an iStoreWriter. But if you look at the composition changes because the writer is now still a composite store writer, but if you look at the inner writers that are being passed to the composite, it's now a new locked saving store writer, then the variable C, and then a new locked save store writer. The variable C is a new store cache. You can see that in what the lines above. The store cache implements iStoreWriter, so that's why we just did that. But store cache also takes an iStoreWriter as input, and that's the file store in this case. So we compose the file store into the store cache because file store also implements the iStoreWriter instance. But we can do this again. Now we just applied the decorator pattern to the store cache, but we can also apply it to the store logger. So the logger was the class that we had problems with before because we couldn't implement iStoreWriter with store logger because we couldn't choose between the saving and the save method, and you can't implement the same interface twice in the same class. So that's why I had to create those microservices before that. You probably didn't like them. I don't like them either. But now if we make store logger a decorator of iStoreWriter, then you can actually solve the problem. So before I make store logger a decorator, I'm just going to show you that I have nothing like nice behavior, that store logger is just what you see in this, just a little basis in the bottom of the screen here. So the first step is to make store logger implement the iStore writer interface itself. And that's trivial to do because the iStore writer interface defines the save method. So we have to add the save method, but we can make it a no-op. So this is a degenerate implementation of iStore writer, but it compiles. It doesn't do anything, it doesn't add any value, but it compiles. Now this is not decorated yet because it doesn't compose another store writer, but that's the next step. So now we add a constructor that takes an iStore writer as input, and we assign the writer to a field. So the next step is to call that writer from the save method. So it's no longer a no-op, but it's still not a particularly interesting implementation of the save method because it doesn't really add any value yet. But now we can start adding value because before and after we call this writer save, we can log the information. So we log the information that the message has been saved before we call this writer that saved, and then we log the information that it was saved. And if you've ever heard about a technique called aspect-oriented programming, this is what aspect-oriented programming is about. AOP, as it's also called, has a strange terminology, but this particular way of having an aspect is called an around advice. And the reason why it's called around is because we have behavior that we add around the inner core, if you will. And if you recall back to the store cache decorator that I mentioned before, that's also an advice. It's not a round advice, but an after advice, because all the extra behavior that's being added by the store cache happens after the call to list of writer save. And there's also something called a before advice as well. That's not particularly important though, but I think it's very interesting when you can pull in terminology from other pieces of computer science and then relate those two things together. So now that the store logger also inputs iStore writer and decorates iStore writer, we can change the composition again. So now this writer is being assigned a new composite store writer that just takes L as input, and L is a new store logger. And store logger is the class that we just made a decorator of iStore writer. And it decorates the variable C, which is the store cache, that just like before implements iStore writer, and the store cache again takes iStore as input, because FileStore already implements iStore writer. So the last assigned here, this writer equals new composite store writer of L. The composite is now redundant, and we just throw it away and just assign the L variable to the writer because the L is also an iStore writer. So what really happens here is almost like Chinese boxes, or those Russian babushka dolls, where you open one box or you open up one babushka doll and there's another one inside of it, and you open that one and there's another one inside of it, and you can keep on going for quite a while until you reach the core of whatever is being composed. So that's the decorator. It's also sometimes called the Russian doll model. That was